So here we're looking at absolute value functions and their graphs on the coordinate plane. So the idea behind an absolute value function is where x, the dependent variable, is inside of the absolute value. Now there can be more stuff going on, as we'll explore over the course of the next couple of lessons, but the bottom line is x has to be inside the absolute value, and then the f of x, or y if we want to treat it that way, is on the other side of the equation. So the focus here to get started is to make sure we understand what the graph looks like. And so hopefully this is at least somewhat reminiscent of work we've done earlier, but the graph of an absolute value function turns out to always be a V shape of one sort or another. Now, we'll start with kind of our basic, just absolute value of x. There's no other numbers, multiplying the absolute value, adding or subtracting, inside or outside. It's just our, what we'll refer to as our parent graph. So this is the parent graph that we're going to be working on. And so we're going to graph this using a t-table, but we're very quickly going to move away from the use of a t-table because we're going to be able to base everything off of this initial graph. But to get us started, I've just got a simple t-table here. So -2, if we plug that in for x, hopefully we remember that when you take the absolute value of a number, it's always positive. Absolute value is a measure of a distance from 0. Distance is always positive. So therefore, absolute value of -2 is going to equal 2. So I can go to -2, up 2, and make a dot. If I plug in -1 for x, the absolute value of -1 is going to turn it into a positive, so I'm going to get +1. So same thing, left 1, up 1. If I plug in 0, the absolute value of 0 is 0. Pretty simple there. So now we're at the origin. But then this is where the V shape starts to take place, because now when I plug in 1 for x, the absolute value of 1, it remains positive, so there's no change, so it stays as 1. So I'm over 1, up 1. And then finally, if I plug in 2, absolute value of 2 remains 2, so we're up 2. So now we've got our V shape for our graph. And so again, this is the parent graph that we're going to use. This is what we're going to base all of our other graphs off of as we start to move it around the coordinate plane due to the introduction of various constants in various locations in our equations. So here we see the first place where we can introduce a constant. So we can add or subtract a number outside of the absolute value. So what we can see here in the two examples, in the first one we've got a -4, and the second one we have a +2. But in both cases the absolute value of x is intact, and then we're adding or subtracting a number outside. And so what we're going to find is if we add or subtract a number on the outside, it's going to move the V shape up and down. Now we're going to use a t-table to help us see that in one more example, but after this we're going to do away with the t-table and we're just going to rely on our understanding of how the introduction of these numbers moves the graph around without having to plug in a bunch of numbers. But for this one we'll stay with that. So if I plug in -2 for x, the absolute value of -2 is 2. 2 minus 4 gives me -2. So I've got -2 for x, I've got -2 for y. Now I plug in -1. Take the absolute value of -1, I get 1. 1 minus 4 is -3. So hopefully we're starting to see that we're following the same pattern. I'm left 1, down 3, and then if I plug in 0 for x, absolute value of 0 is 0. 0 minus 4 is -4. So I've gone down once more, but now this is where we're going to see the rebound, because the absolute value of 1 is the same as the absolute value of -1, so it's 1. 1 minus 4 gives us our same result of -3, and then plugging in 2 is going to give us the same result as -2. Absolute value of 2 is 2. 2 minus 4 is -2. So we've got these two additional points here. So we're getting that exact same V shape. The slopes of the two sides are 1 and -1 respectively. It's exactly the same as the original. It's just now all of the points have been translated down 4 units as a result of that -4. So when it says here transformation. We're trying to describe what has happened to the graph. And so we can say that the graph has been translated, which is another way of saying to slide something. So it's been translated down, down 4 units. So the presence of that -4 outside the absolute value moves the graph down 4 units. Well, if subtracting this 4 moves the graph down, then it should make sense that adding 2 outside of the absolute value should move the graph up 2 units from its original position. So this time I'm going to do away with the t-table entirely. And I'm just going to say, all right, instead of starting at the origin like this first graph did, I'm now going to take my point of the v and move it up 2 units because of the +2. And then from there, I'm going to keep the exact same shape of the v with the slopes of 1 and -1 on each side. So I can go up 1 over 1, up 1 over 1 on one side, back 1, up 1, back 1, up 1 on the other side, and end up with my graph. And I can confirm that by plugging in a couple values for x if I wanted to. If I plug in 0 for x, I'm going to get 2 as an output. You can see the bottom of the v is right here at 2. If we plug in 2 for x, absolute value of 2 is 2, plus 2 is 4. So that's going to give me this location right here. So the shape of the v is not being affected. The width or how steep the sides are, how wide it is not being affected. It's just the starting point that's moving up and down as a result of this plus k. So as long as that number is positive, the graph is going to move up. As long as that number is negative, the graph is going to move down. And so in this case, we can say that the graph was translated up 2 units.